Hello, we are Team Socks from Raffles Girls' School. We are going to talk about our experiences participating in soccer this year. We will start with the team introduction, followed by a breakdown of our hardware and software. Firstly, an introduction to our team. Cadence is our team lead. She and Euro are in charge of software. Rebecca and I are doing hardware. To start off, we will be talking about the hardware portion of the robot. For the construction of our robot, we used one OpenMV camera, a V-shaped mirror, 4 Joinmax ultrasonic sensors, and 2 compound eyes. We also used 4 Joinmax Omni wheels and motors, 1 compass, LED lights integrated into the bottom plate, and 9 𝑹𝒐𝒃𝒐𝒐 sensors for each robot, which can be seen in the photo here. Each robot also has a battery gate, a 5-volt voltage regulator, a Joinmax motor driver, and 2 𝗃𝒂𝒂𝒑𝒐𝒓𝒆3.5s. Here is the layout of our wiring. The 12-volt battery supplies power to the motor in order for the motors to run and also powers a 5-volt regulator. The 5-volt regulator then steps the 12-volt signal down to 5V in order to power the motor driver itself, as well as the remaining components on the robot such as the sensors and 𝗃𝒂𝒂𝒑𝒐𝒃𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂𝒑𝒂 𝗕6000 so as to maximize the processing rate of the microcontroller and allow the values the 𝗕6000s are sensing to be read quickly. All other processing was done on the other TNZ. This allows the robot to react at a faster rate to the boundary lines, which is important in boundary control as if the robot reacts too slowly, it would go out of bounds. The sensors record and send information to the TNZ 3.5s either by 𝐼²𝐶, serial communication, or analog. 𝗕6000 sensors will send analog readings to the second TNZ. TNZ 2 then processes the 𝗕6000 input and the angle at which the robot senses the line is calculated. This is so that the robot can move in the opposite direction of the line, and the corrected angle is then sent to the main TNZ. The other sensors connect to and communicate directly with the main TNZ. We used the plates that we designed last year and finished creating the PCBs during the December school holidays. The PCBs were created in Easy EDA. We designed the PCB plates this year such that wiring would be less of a hassle since we could directly plug in the electronics without having to refer to a wiring plan. Using PCBs also enabled the 𝗕6000s to be directly soldered onto the bottom plate without wiring. We decided to use a 4-wheel omnidirectional drive base as this allows the robot to travel in multiple directions as well as change direction rapidly depending on the speed and the acceleration of each wheel. Furthermore, a 4-wheel drive base allows maximum amount of force to be exerted by the motors in order for the robot to move, whereas if a 3-wheel drive base is used, a smaller resultant force will be obtained. For example, if the robot is traveling in the direction of 0 degrees, in a 4-wheel drive base, the motors at the back will also be moving and exerting a force on the robot. Whereas in a 3-wheel drive base, the motors at the back will not be moving and contributing to the movement of the robot. Hence, a 4-wheel drive base allows the robot to travel at a faster speed. Thus, we designed the plates based on this decision. On the bottom plate, we soldered 𝗕6000s and mounted our motors as the LEDs were already integrated onto the PCB. The 𝗕6000s are positioned as low as possible to be closer to the field so that the difference in color is easily detected and that there are no other components blocking the 𝗕6000 sensors. On the middle plate, the motor driver and main PCB are mounted. The motor driver is mounted high enough for the battery to fit below it, but as low as possible in order for the robot to fit within the height limit of 22 centimeters. We designed the middle plate such that a PCB gate could be attached to the side of the plate to fit the battery in easily. This is because in our previous robot from 2021, the 3D printed gate kept breaking and we decided that using PCB material to make the gate would make it more sturdy. The main PCB was also designed such that it could be placed at the same height as the motor driver, allowing us to reduce the height of our robot.
On the top plate, the ultrasonic sensors, compound eyes, mirror, and camera are mounted. The top plate is smaller than both the middle and bottom plate. It follows a skeletal outline, which means that we only have material where the mounting holes are in order to reduce the weight and stay within the weight limit of 1.1 kg. The camera is mounted on the top plate of the robot as this allows the camera to be as high as possible in order to see the mirror without obstructions to its field of view. For the compound eyes, we place them such that the rays from the bulbs of the compound eyes will not be obstructed by protruding wires. We also mounted them from the top plate so that they will be high enough to detect the ball. This year, we redesigned and 3D printed our mirror mount. The mirror allows the camera to view the opposite ends of the field where the goals are located, in order for aiming to be implemented. It also has to be constructed such that the rays of the camera reflect off the mirror to form parallel rays, allowing the camera to see into infinity. In order to determine the angle of the mirror, we had to use various calculations involving the field of view of the mirror, which is 55 degrees. Calculations were done in AutoCAD. A V-shaped mirror is used in order to see both ends of the field, as when the robot is facing forwards, it will only need to see both ends of the field in order to aim. Next, we will be covering the components we used as well as their purpose. We decided to use the 𝗃𝒑 3.5 as it was much faster than the Arduino board in terms of processing. The 𝗃𝒑 3.5 has a clock speed of 120 MHz, while Arduino Uno has a clock speed of 16 MHz, meaning that the 𝗃𝒑 3.5 has a higher processing speed than the Arduino Uno. Furthermore, the 𝗃𝒑 3.5 is also much lighter and more compact than the Arduino Uno processor, allowing us to reduce the robot's weight. The two compound eyes are placed such that they cover 360 degrees, allowing the robot to be able to detect the ball coming from any direction before responding to the ball. The height at which the compound eyes are mounted is also important, as mounting them too high above the ground would result in the robot not being able to detect the ball in the ball capture zone. And they cannot be mounted too low as their view will be blocked by protruding wires, causing the robot to be unable to detect the maximum IR intensity when the ball is near the robot. Hence, we decided to set the maximum IR intensity in our code to 135 in the ball capture zone and 110 around the robot, as these were the maximum intensities we got when the ball was placed as close as possible to the robot. Thus, if the robot senses these maximum intensities, it will take the position of the ball to be the closest possible position. The robot detects the boundary lines by utilizing 9 light sensors which are 𝒃𝒐𝒴. When detecting the values using ambient light, the signal-to-noise ratio is low. This causes the values to fluctuate greatly, and hence makes the readings less reliable and consistent. The total reflected light intensity regardless of color is also very low if only ambient light is used. Hence, there will be a lower difference in the 𝒃𝒐𝒴 values for green field and the white boundary line. However, if the robot uses LEDs in order to light up the ground below it as the robot travels, there is a larger contrast between the values recorded for green and white since the white reflects more light than green, and it will also not have to only rely on ambient light which varies according to the surrounding environment. We also use red LEDs as red is complementary to green, allowing there to be a greater difference in the values detected by the temps. This in turn reduces the likelihood of error. Previously, we zip-tied an LED ring near the 𝒃𝒐𝒴 in order to light up the ground. However, we decided to switch to integrating the LEDs into the PCB bottom plate instead of using LED rings, as it would reduce the hassle of having to attach it securely to the robot. The ultrasonic sensors are mounted on the top plate using 3D printed mounts. Because the ultrasonic sensors return an analog voltage and not a distance in terms of centimeters or millimeters, we had to convert the readings obtained by the ultrasound to obtain distance from volts. And to do so, the voltage readings from an ultrasound at various intervals of a measuring tape were taken. For example, intervals of 10 cm, 20 cm, and 30 cm. We then plotted the graph in order to determine the conversion of values from volts to centimeters, which was then converted to millimeters in the code. Previously, we used a newer model of ultrasonic sensors, MB1010. However, the maximum distance our sensors could sense reliably was not enough. Hence, we decided to use more consistent JointMax GMPBE 6302 ultrasonic sensors. Originally, the robot used one ultrasonic sensor on each vertical and horizontal axis to try and pinpoint the location of its field. However, the reading from one ultrasonic sensor on each axis is insufficient as the robot is unable to tell if it is being blocked by another robot on the other side which does not have an ultrasonic mounted. Hence, the area that the robot could be in is very large. Thus, we decided to use two ultrasonic sensors on each axis. This means that there is a pair of ultrasonic sensors facing the front and back, as well as a pair of ultrasonic sensors facing the left and right of the robot. By taking into account the total distance sensed by the pair of ultrasonic sensors on each axis, the robot is able to determine if it is being blocked and adjust accordingly. For the older model, using two sensors from each axis was useful as the maximum distance that the sensors were able to detect was around 1.4 meters. So if the robot was too far from the walls, the other sensor would be able to tell the robot its position. We also use the camera and mirror to find and aim for the goal once the robot gains possession of the ball by using color block tracking. The camera is mounted on the top plate, and it is the highest component of the top plate so that it will not be obstructed by any other components on the robot.
Now, we'll be going through the software aspect. For our code, we use Arduino and OpenMV for the camera. As for the strategies we use in our code, we have two separate robots, one being the Striker and one being the Goalie. So firstly, the Striker. The logic is as follows. Firstly, if the robot senses the line, it will move in the opposite direction of the line. If not, the robot orbits the ball with the balls in play. The angle and speed at which the robot orbits the ball is then constrained by the distance from the boundaries and the robot's confidence of its position. If the robot is unable to detect the ball, it returns to its home. For movement, we implemented a function that allows the robot to move in any direction and at any rotation rate using a four-wheel drive base. This was done through the use of trigonometry and resolving forces. At 0 degrees of the robot is the ball capture zone. The direction is first offset by 45 degrees so that the motors are on the x and y axes. The motor should be 45 degrees from the axis, so that value is used. Resolving the direction to x and y components allows the speeds of pairs of motors along the x and y axes to be obtained. The motors are then run at these values, and there is a resultant force acting on the robot, causing it to move in the specified direction. A rotation rate is applied to the movement function based on the angle the robot needs to turn to face 0 degrees. Since each pair of motors acting along the same axis are equidistant from the center of the robot, within each pair of motors, when the motors are moving at the same speed, there is no resultant torque on the robot, as it has equal counterclockwise and clockwise torque. Hence, to rotate in either the clockwise or counterclockwise direction, we vary the speed of one motor in order for there to be resultant torque, causing the robot to rotate in the specified direction. As for determining the position of the ball, we implemented a function that allows the robot to identify the angle of the ball and move towards it. Since each compound eye has 7 ports to cover an angle of 180 degrees, by using 2 compound eyes, we end up with 14 bulbs in total with 2 overlaps, covering 360 degrees. Thus, there are 12 unique directions that the ball could be in. However, simply taking into account the angle of the port with the maximum IR value and hitting that direction will make the movement unsmooth, as the robot will have to constantly make drastic changes in direction. Hence, the robot takes into account the IR values of the port on the left and right of the port with the maximum IR value. By finding the ratio of the difference between left and middle IR values and the difference between middle and right IR values, we can accurately interpolate the angle of the ball. Hence, the angle is resolved to a greater resolution. This allows the robot to have smoother movement with less sudden changes in acceleration, making the overall movement more efficient. In the case where the robot is unable to sense the ball, or in other words, when the IR intensity is very low and the ball is out of the field, it will return to the middle of the field and proceed from there, and this will be elaborated on later as well. Since the aim is to get the ball into the opponent's goal, the robot first needs to move the ball towards the opponent's half of the field. In order to better control the ball to move in that direction, the ball capture zone should face towards the opponent's goal. This is because the ball capture zone of the robot provides a better surface for the robot to control the ball, increasing the chances of scoring. The robot needs to take the shortest time to reorient itself so as to allow it to quickly continue to score. In the case of the goalie, this allows it to quickly continue defending the goal. To achieve this, we implemented compass correction. We obtained the angle the robot is facing from the compass reading, and the robot will rotate either clockwise or counterclockwise, whichever is shorter, to face the opponent's goal. Additionally, the rate of rotation of the robot is proportionally controlled by the difference between the compass reading and the set hitting, 0 degrees. When the robot is more tilted and the difference is higher, the robot turns to face 0 degrees at a higher rate of rotation, allowing the robot to correct its orientation and face the opponent's goal in the shortest possible time. The ideal situation would be for the ball to enter the ball capture zone of the robot while the robot is still facing the opponent's goal. The ball capture zone is slanted so as to allow for the ball to be centered in the middle as the robot travels, regardless of the angle the robot is traveling at. When the ball is out of range of the ball capture zone, the angle that the robot moves towards is corrected by the IR intensity scaled by 90 degrees. This allows the robot to orbit the ball more aggressively so as to prevent the robot from contacting the ball with other parts of its body, and hence reaching a favorable position from which it can directly intercept the ball. For example, in the instant where the ball is 90 degrees to the robot and is directly next to the robot, the intensity the IR's return will be high, and the robot moves in the 180 degrees direction in order to orbit the ball and have the ball lie within the range of the ball capture zone. When the ball is within the range of the ball capture zone, the robot does not need to orbit the ball and can instead move directly towards it. The result will be the robot moving at an angle that allows the ball to be controlled within the middle of the ball capture zone. This allows the robot to have better ball handling and reduces the chances of the ball accidentally sliding out of the ball capture zone. We use compound eye readings to determine if it's in the ball capture zone, taking into account both the intensity and angle of the ball. If the ball is within the range of the ball capture zone and the compound eyes give a high IR reading, the ball is likely to be in the ball capture zone. After the robot is able to gain and maintain possession of the ball, the next step would be to score a goal. This can be done through the use of aiming. Without aiming, the robot will only be able to move the ball towards the opponent's end of the field, but may not actually score a goal. In order to score a goal, the robot needs to accurately determine the position of the goal relative to the robot. and hence determine the angle it needs to move at in order to score. We decided to use a camera and mirror in order to determine the location of the goal relative to the position of the robot. This was coded in the OpenMV IDE. Using the camera's advantages, it has a wider field of view than the ultrasonic sensors. Hence, even if the robot is being blocked, there's a high chance of the camera being able to see the goal, allowing the robot to attempt to aim. The camera is also able to detect the largest blob of color of the goal, signifying the largest open area of the goal, and aim towards that. And as a result, even if there's a goalie defending the goal, it will still be able to see part of the goal too. Furthermore, this method does not require the robot pinpointing its exact location, and instead relies on finding blobs of color of the goal, which is yellow or blue, using thresholds in order to find the angle the robot should be traveling at to reach the goal. Hence, even if the robot is being blocked, the robot is still able to head towards the goal. However, there's always room for error. In the case where the camera is unable to see any part of the goal and has possession of the ball, it will revert to using localization-based aiming in order to move towards the goal, which will involve using the ultrasonic sensor readings to read towards specific target coordinates, in this case, the middle of the goal. This will allow the robot to still attempt the score, and will be elaborated more on later. To ensure that the robot does not go out of bounds, we determine the robot's position by using two ultrasonic sensors for each axis. In other words, there's a pair of ultrasonics facing the front and back, as well as a pair of ultrasonics facing the left and right of the robot. When the robot senses that it nears the boundaries, it should move.
After detecting the ball, the robot will want to move in a certain direction at a certain speed. Using these values, the speed can be resolved to its x and y components, and we know which direction the robot will be moving in, and the speed can be constrained accordingly based on the robot's distance from the boundary in that direction. If the robot is moving in the leftwards direction, the distance from the left boundary is considered, and the speed of the robot is reduced proportionally from its distance to the boundary. This allows the robot to stop before it exceeds the boundaries. If the robot isn't blocked, we are able to determine its exact location based on the distance between the robot and the walls of the field. However, if the robot is blocked and it cannot pinpoint its exact location, the sum of the distances detected by the sensors would not be equal to the dimensions of the field. For instance, if the robot was blocked on its left, the sum of the distances that the left and right ultrasonic sensors detect would be less than the width of the field. The robot can then determine a possible area in which it could be located. By using the ultrasonic readings, we can determine how confident the robot is of where it is on the field. When the sum of the readings of each pair of sensors is smaller, the area that the robot could be in is larger. Thus, it is harder to determine the exact location of the robot, and it will be less confident of its position. The robot will then move slower in that axis. Besides the usage of ultrasonic sensors, the robot ensures that it does not go out of bounds by detecting the boundary lines. It utilizes 9 light sensors or 𝒃6000 to do so. When the robot senses the white boundary line, it moves in a direction opposite to the sensors detecting the line until the robot is certain that it is within the boundaries, helping it to avoid going out of bounds. In addition to the aforementioned functions, the robot also needs to be able to accurately move to certain target coordinates within the field. This will be used in 2 different cases. The first is when the robot is unable to sense the ball and needs to head towards the middle of the field. It does so as this puts the robot in a more advantageous position to be able to sense the ball in any direction and move towards it from there. This is also used in the case where the robot is in possession of the ball but the goal is not within the field of view of the camera. In this case, we would have to revert to using localization-based aiming. That is, the robot would have to move towards the middle of the goal in order to score. In order to move towards the target coordinates, the robot first pinpoints its location on the field using the 4 ultrasonic sensors. In the case that the robot is being blocked, the robot will take the middle of the possible area it could be in as its coordinates. From there, knowing the target coordinates, the robot is able to determine the angle it should travel at, as well as the distance it needs to move at in order to reach its target. From the distance that the robot needs to travel, we can use proportional control in order to determine the speed the robot should be running at. In other words, the robot moves at a faster speed the further away it is from the target, and slows down as it approaches its target. This prevents the bot from overshooting its target position and skidding. The target angle and the speed will then be inputted into the movement function, allowing the robot to travel to its target. This function was used to cycle the board in a technical challenge. Here's a video of the striker returning to the center of the field when it cannot detect the ball. Next, for the goalie, it needs to prevent the opponents from scoring goals, and it does that by blocking the ball when it approaches the goal. The capabilities of the goalie are similar to the strikers. That is, the robot must be able to move towards the ball to intercept it from the opponent and stay within bounds. However, some modifications must be made to use the robot for defense. In order to guard the goal, the goalie moves towards the ball to block it from the goal when it is nearby. The goalie stays near the goal in order to be able to quickly defend it. This is different from the way the striker consistently tracks and chases after the ball. The difference between the goalie and the striker is that the IR threshold for the goalie is increased. This is to ensure that the goalie stays near the goal at all times and does not move unless the ball is very close to it. When the ball is closer to the goalie, there is a higher chance that the opponents are in possession of the ball and are moving it towards the goal to score. Thus, the goalie should respond by moving towards the ball to intercept it. When the IR intensity is below the IR threshold, the goalie would not react to it. Another difference is that the goalie returns to its home, which is the position in front of the goal, if the ball is not detected, and does so using the function that we mentioned earlier to move to the target coordinates. This is to ensure constant defense should opponents attempt to score a goal. In the scenario on the right, the goalie will be unable to detect the ball, hence the goalie will return to the goal. We will now be talking about how we want to improve on our robot. As of now, throughout the game, there will be one striker and one goalie robot. However, in the future, we hope to implement a goalie-to-striker or striker-to-goalie transition in order to be able to score more goals. For goalie-to-striker, we intend to implement it when the goalie is in possession of the ball. This is because if the goalie is already in possession of the ball, it should be taking the opportunity to attempt to score instead of simply hitting it away from the goal. As for the striker-to-goalie transition, this will be implemented when either the goalie is attempting to score or when the goalie is out of play, in order to ensure that there is constant defense in front of the goal. However, the striker-to-goalie transition will require Bluetooth communication between both robots, which we would also have to take into account in the future as we are not currently using any communication between both robots. Another improvement we want to make is implementation of a light gate in the ball capture zone, where a beam of light is shown across the ball cap zone, which is blocked when the ball passes through, and this change in light intensity is detected by a 𝒃6000 sensor on the other side of the ball capture zone. As of now, we are using only IR values to determine if the ball is in the ball cap zone. However, this may not be very reliable since the IR values can still be high even with the ball outside the ball capture zone. Hence, by using a light gate, we can achieve better detection of the presence of the ball in the ball cap zone. To wrap this presentation up, we will be reflecting on our learning experience from the past months of preparation for this competition. From this competition, we've learned the importance of teamwork and adaptability, especially with the changing COVID situation. We also realized the importance of time management as this was critical in allowing us to complete the robots. It was important to have a plan before starting and follow the timeline closely to ensure that we are on track. Lastly, we realized that the process is more important than the result. While it is satisfying to see your robot finally work after spending months on end building it, we realized that the process we had taken in order to achieve that was much more meaningful. Throughout this entire RoboCup journey, we have learned many new skills and knowledge in terms of both hardware and software, and this competition has indeed been an enriching experience for us. Before we end, we would like to thank our teachers and friends for helping and supporting us throughout this entire journey. We hope you enjoyed our presentation. Thank you for listening.